Good afternoon, everyone, and welcome to my talk towards in situ visualization and virtual surgery in nasal cavities. Before I start with my talk, I would like to thank the organizing committee for inviting me to this conference, and I would also like to introduce my co-authors, which are Dr. Andreas Lintermann and Professor Wolfgang Schröder. So the work I will present today was done in the frame of the project RhinoDiagnost, which aims to bring new diagnostic methods in rhinology to clinical application. And those diagnostic methods are, on the one side, in vivo diagnostics with the 4-phase rhinomanometry as shown here, and then in silico diagnostics with the geometrical analysis of the nasal cavity with, for example, three-dimensional surface geometries of the nasal cavity, and with interactive supercomputing with numerical simulations and the virtual nose surgery, about which I would like to talk today. The rest of the talk is structured as follows. I will present the numerical methods we used. So first the automated simulation pipeline and then the level set method, which we need for the virtual surgery. Then I will present the results we obtained for the live visualization and also for the virtual surgery, and give a short conclusion and an outlook. So here you can see the automated simulation pipeline for respiratory flow simulations. It starts with the upload of CT data sets of a patient, which are then automatically segmented by a machine learning approach. And then the segmented data sets are used for the geometry generation of a three-dimensional watertight surface geometry, which is then used to generate an unstructured hierarchical Cartesian mesh on which the Lattice-Boltzmann method is used to solve the respiratory flow. And we need that many cells because we perform scale resolving simulations, so we don't use any turbulence modeling but resolve all the structures of the flow directly. And live at runtime, the outcome of the simulation is visualized using ParaView Catalyst. This is shown here in the last part. And the whole pipeline is accessible using a Jupyter Notebook in a web browser application. So also users who don't have any knowledge about high performance computing can use this pipeline. So now I continue with the level set method, which can be used to store an arbitrary body in a discrete form using the signed level set function. And this is shown in figure 4. So for each cell, the minimum wall distance is stored, and the sign of this value decides whether the cell is inside or outside. And for the virtual surgery, we now first create a pre-surgical nasal cavity from the CT datasets, and a post-surgical nasal cavity is created by the user by modifying the pre-surgical one using a software like 3D Slicer. And then for the simulation, both of those geometries are represented by a level set function, and then the flow simulation is started in the pre-surgical nasal cavity, and after a certain time step, then by an interpolation, the geometry is transferred from the pre-surgical state to the post-surgical state. And since the flow simulation is done in the meantime, the properties like the pressure loss, for example, are evaluated for during this modification. And so the user can see how the pressure loss develops during this modification and find a surgery that is better than his initial surgery. Okay, now I come to the results, and I start with the results of the live visualization. So here you can see plots that are plotted live during the simulation, and you can see the simulation data, so the pressure loss and the temperature along this geometrical center line here for the left and for the right cavity of the nasal cavity. And those values are calculated on slices which are orthogonal on those on the center line in an equidistant distance. And on those slices, these values are averaged and then plotted on this curve. The second option to visualize the data is using ParaView Catalyst as shown here. So here we have the simulation output for time step 65, 70 and 75,000 in the pharynx region, and you can see how some vortex structures in this region develops, so you can monitor the simulation progress in pictures and not only in plots. And here you can see the results of the virtual surgery. So as already explained, we have the pre-surgical state with a bone spore here, and this bone spore is removed by the virtual surgery approach. So this is a post-surgical state, and here we have a state in between due to the interpolation. And as you can see, we have here some high velocity area, and this velocity is reduced here and also here, but between those two states there is nearly no difference, and this shows us that it might be enough to reduce half of the spore instead of the complete spore, which is a great advantage of our virtual surgery approach. So now I come to the results. We have seen how the in-situ visualization works and how we can inspect simulation data with it and monitor the simulation progress. Then we have seen how the virtual surgery approach works, which is based on a lattice-Boltzmann method coupled to a level set method. And in the future, we want to accelerate our method by porting it to GPUs. And that will increase the advantages of the live monitoring since the simulation time is reduced. Furthermore, we want to implement computational steering to further improve our virtual surgery approach and give the user more possibilities. Thank you very much for your attention, and now I'm happy to answer your questions.